Hey guys, today we're going to learn about the mean value theorem and Rolle's theorem. Let's start with the mean value theorem. Now this is the formal definition of what the mean value theorem is. If f of x is continuous on the closed interval a to b, that's why we see the brackets, and differentiable on the open interval a to b, that's why we see the parentheses, then there is guaranteed to exist a value of c on the interval a to b such that f prime of c is equal to f of a minus f of b over a minus b. So let me dissect what this is saying. Before, just like we did with the extreme value theorem, we have to determine whether the mean value theorem would be applicable, which would be those two conditions. One, that it is continuous on the closed interval a to b, and differentiable on the open interval a to b. And if that is true, then we will have a value of c on the open interval a to b, meaning that this value is not going to be any of the endpoints, such that the derivative is equal to the slope of the secant line, which we've done the slope of the secant line before, we've done the derivative before, so all the mean value theorem is stating is that these two things are equal, since we have learned in the past that the slope of the tangent line is very, very close to, if not equal to, the secant line. So a couple of things to keep in mind. Whenever you see the words average rate of change, this represents the slope of the secant line, which is when we use the slope formula. In Algebra 1 and Algebra 2, slope formula is y2 minus y1 over x2 minus x1. This is the same exact thing, just different notation. Here we use the function notation. If you see the word instantaneous rate of change, that is the slope of the tangent line, which is the derivative. So basically, MVT is just stating that these two things at some point will be equal if it satisfies those above conditions. So now let's look how we would apply MVT. Before we even apply it, we're going to check if it is applicable. So here we have this function, f of x is equal to 3 minus 5 over x, and we want to check if it would be applicable on the interval -1 to 5. Now, -1 is over here, but you can see here from the graph that there seems to be some kind of vertical asymptote here at x is equal to 0, which when you look at the equation, we do have a denominator that contains our variable, meaning that x, my denominator, cannot equal to 0. Therefore, there's a break in continuity which lies in this interval at x is equal to 0, because 0 is between -1 and 5. So it does not satisfy that first condition. So here we would state that f of x is not continuous on the interval -1 to 5. And if that's the case, then MVT is not applicable and we cannot go any further. However, here, if we change the interval to 1 to 5, then MVT guarantees a value of x is equal to c, where the tangent line drawn to f of x is parallel to the secant line passing through the point 1, -2, and 5, 2. See, here is 1, and you can see that the coordinate is 1, -2, as stated here. And then here's 5, which is the coordinate 5, 2. So what we do here, if we're going to apply MVT, first we have to state here my function is continuous. So f of x is continuous on the interval 1 to 5. That's the first condition. The second condition is that it is differentiable. How you know based on looking at a graph if it's differentiable or not, you don't see any cusp. When we see a cusp, that means that it is not differentiable at that point. Therefore, since everything is nice and smooth, we can then state that f of x is differentiable. And this one is on the open interval 1 to 5. Once we have shown that these two things are true, then we can confidently say that MBT is applicable. What we do from here, if MBT is applicable, then this means that f prime of C is going to equal to f of A minus f of B all over A minus B. Now you don't need to write this every single time. However, if you do find it helpful, then by all means. I'm writing this now just so that you can see what we're going to do. For this part here, for f prime of C, I have my equation. So what I'm going to do is I'm going to take the derivative of that equation. First of all, what I can do, instead of applying the quotient rule, I can bring the x up. So this is going to be 3 minus 5x to the negative 1. Now I'm going to take the derivative. So f prime of x is going to equal to, the derivative of 3 is 0, and then here I'm going to take this negative 1, multiply it to the negative 5, so that's 5x, and subtract 1 to the negative 2. Therefore, f prime of x is going to equal to 5 over x squared. So this is my derivative. Now keep in mind that MBT is asking you to solve for a value of C. So notice here my notation is f prime of C. So I'm going to replace the x with c's to remind me that I am solving for C. So f prime of C is going to be 5 over C squared. And I'm going to make this equal to f of 1, that's my A, minus f of 5, which is my B, all over A minus B, so 1 minus 5. And I'm going to get these values from the graph. F of 1 is negative 2. So negative 2 minus f of B, which is 2, all over 1 minus 5, which is negative 4. So now what we have is 5 over C squared is going to equal to negative 4 divided by negative 4, which is 1. To solve for C, since it is in the denominator, I am going to multiply C squared to both sides to remove it from the denominator. And I get here that 5 is equal to C squared. Then to solve for C, we're going to square root both sides. So C is going to equal to plus or minus the square root of 5. Since remember, anytime you square root, it's always plus or minus. Now, normally there's only one value of C. There could be more, but we have to look at the interval. The interval is from 1 to 5, and this value of C has to be within the open interval. So it has to be in between 1 and 5, not including those endpoints. Positive square root of 5 is within that interval. So C is going to equal to the positive square root of 5. Where negative square root of 5, it's outside that interval, so we would not count this one. So my only value of C here would be positive square root of 5. And this is basically the entire process of MBT, but we're going to break this down a little bit more before doing some more sample questions. So as stated before, just like we do with EBT, we need to determine whether the mean value theorem is applicable on the given interval. Here I have the function f of x is equal to x plus 1 over x, and we want to see if it is applicable on the interval negative 1 to 2. So first we have to determine whether it is continuous on that interval. Since I have x in the denominator, this means that x cannot equal to 0. Now 0 is within this interval because 0 is between negative 1 and 2. Therefore, f of x is not continuous on the interval -1 to 2. And because it is not continuous, it breaks that first condition of MVT. So we can state here that MVT is not applicable. Now for the second one here, explain why you cannot apply the mean value theorem, MVT, for f of x is equal to x raised to the 2/3 minus 2 on the interval -1 to 1. Now, whenever you have a variable raised to a rational exponent, remember that the numerator tells you the power of that variable and the denominator tells you the root. So what this is f of x is equal to the cube root of x squared minus 2. We've learned that when you have a square root, you can never have a negative inside of that radical. However, when you have an odd root, such as a cube root or a fifth root or a seventh root, you can have any number within that radical, because remember that a root tells you that you're looking for however many of that identical number in order to remove it. Well, with a cube root, so like let's say, for example, the cube root of -8, -8 can be broken down to 4 and 2, and then 2 and 2. If I make these all negative, -2 times -2 is +4, and times the third -2 would give you -8. So we are allowed to have negatives inside of a cube root. So what this means is that any variable raised to a rational exponent where you have an odd number in the denominator is always continuous. So let me show you what that graph looks like so you have a visual. This is that graph. And you can see that from -1 to 1, it is continuous. I can trace the entire thing without lifting my mouse. So therefore, this would be considered continuous. However, what we do see here is a cusp, meaning that it's not going to be differentiable. And that's the second condition of MVT. Now granted, this is a question where you would not have the graph, so we would have to be able to figure that out. So before moving on, I would clearly state that f of x is continuous on the interval -1 to 1. But now we're going to determine differentiability. So differentiability means I can take the derivative and I can plug in any number and get an answer. So we're going to take the derivative of this function. If I take the derivative, I would get 2/3 x raised to the -1/3, and then the derivative of -2 is 0. This, I can rewrite this as 2 over 3 cube root of x. Now look at the denominator. I now have my variable in the denominator. So I would put here whatever is in the denominator, 3 times the cube root of x, and it cannot equal to 0. If I divide both sides by 3, 0 divided by anything is 0. The cube root of x is going to equal to 0. And then if I cube both sides, I get that x cannot equal to 0, where that is within the interval -1 to 1. See, we got here that x cannot equal to 0, and that's exactly where we have that cusp. This is x is 0, so it is not differentiable. So we would state here that f of x is not differentiable on the interval. Now remember, this is on the open interval -1 to 1. If the cusp was on either of these values, then it wouldn't matter because those numbers are not included. So, but since 0 is right in between, it's not differentiable on that interval, and therefore MVT is not applicable. So now let's look at an example where MVT is going to end up being applicable and how we would go about to continue that process. Determine whether the MVT can be applied to the function on the closed interval provided. If so, find the value of c guaranteed to exist by the theorem. If not, state why the MVT cannot be applied. First of all, when we look at this function, x to the fourth minus 8x, this is a polynomial function. All polynomial functions are always continuous everywhere. Therefore, we would state here that f of x is continuous on the interval 0 to 2. Next, because this is a polynomial, polynomials are always smooth curves. If they're smooth curves, that means that we're never going to have a cusp. Therefore, we don't even need to see the graph or do anything with the equation. We would know f of x is differentiable on the open interval 0 to 2. Because it is continuous on the closed interval, differentiable on the open interval, this means that MVT is applicable. Now remember, MVT, and I'm going to write this every time, you don't necessarily need to, but just in case, f prime of c is equal to f of a minus f of b all over a minus b. So now I'm going to take the derivative, replacing my x's with c. So f prime of c would be 4c to the third minus 8. And that's going to equal to f of 0 minus f of 2 over 0 minus 2. Now f of 0, when I plug it in, is going to be 0. Minus f of 2, 2 to the fourth is 2 times 2, which is 4, times the third 2 is 8, times the fourth 2 is 16, minus 8 times 2, which is also 16. So 16 minus 16 is 0, all over negative 2. So 0 over negative 2 is 0. So now I make my equation 4c to the third minus 8 equal to 0. And I'm going to solve for c. First, I'm going to add the 8. So 4c to the third is equal to 8. Next, I divide by 4. And I get here that c to the third is equal to 2. Finally, I cube root both sides. When I cube root, my answer is not going to be plus or minus because it's exactly whatever the sign is inside of that radical. It would only be plus or minus if the root that you're applying is an even root. So therefore, my value of c is the cube root of 2. Now, let's move on. Let's try this again with this question. We have here f of x is equal to negative x to the third plus 4x squared minus 5, and we want to determine if MVT is applicable on the interval 0 to 4, and if so, we're going to find the value of c that is guaranteed to exist by the theorem. First of all, we need to go through those conditions of MVT. The first one is that if it's continuous. Since this is a polynomial function, that means that f of x is going to be continuous on the entire interval, because all polynomials are always continuous everywhere. So it is continuous on the interval 0 to 4. Next, I determine differentiability. Once again, because it is a polynomial function, that means that it's all smooth curves. So f of x is also differentiable now on the open interval 0 to 4. Because these two conditions are satisfied, that means that MVT is applicable. Now I'm going to take the derivative, replacing my x's with c. Therefore, negative 3c squared plus 8c is going to equal to f of a, which is f of 0, minus f of b, so f of 4, all over a minus b, so 0 minus 4. Now I'm going to do the work here for my function values on the side. So I need f of 0. If I plug in 0, I get 0 cubed, negative 0 cubed, which is 0, plus 4 times 0 squared, which is 0, minus 5, so negative 5. Then if I do f of 4, 4 to the third is 4 times 4, so 16, times the third 4 is 64, and then we have the negative, so negative 64, plus 4 squared, which is 16, times 4 is positive 64, minus 5. Negative 64 plus 64 would cancel, so we're left with negative 5. So now let's continue here. Negative 3c squared plus 8c is going to equal to f of 0, which I got to be negative 5, minus f of 4, which is negative 5, so it becomes plus 5, all over negative 4. Negative 5 plus 5 is 0, divided by negative 4 would still be 0. So I have my equation here, negative 3c squared plus 8c is equal to 0. I need to solve for c. So here I can factor. Both of these terms have a c in common. So I would get c times negative 3c plus 8 equals 0. If I set each individual factor equal to 0, I get that c is equal to 0, as well as negative 3c plus 8 equals 0. Subtract the 8, I get negative 3c equals to negative 8, and then divide by negative 3. So I get here that c is equal to 8 over 3. Keep in mind, remember what we said earlier, that your value of c cannot be at the endpoints because the MVT only guarantees a value within the open interval, meaning the endpoints are not included. So this c is equal to 0 is not my answer. C is equal to 8 over 3. 8 divided by 3 is 2 point something, which is within this interval. So this would be my final answer. Now we're going to look at Rolle's theorem. Rolle's theorem is actually an extension of the mean value theorem. Now Rolle's theorem always starts off in the same way that mean value theorem is, which is that the function has to be continuous on the closed interval a to b and differentiable on the open interval a to b. So we would still start off in the same way as we do for mean value theorem. The additional condition is that f of a must equal to f of b. And if that's the case, then there is guaranteed to exist a value of c on the open interval a to b such that f prime of c is equal to 0. Now this is why this works. If f of a is equal to f of b, so let's say f of a is 3 and then f of b is also 3. If I subtract, I get 0 over your interval here, and 0 divided by anything would still be 0. So remember that this part here is the mean value theorem. But if f of a is equal to f of b, then that numerator would just be 0, so it would always equal to 0. So essentially, Rolle's theorem is just a special case of the mean value theorem, which is where your derivative must equal to 0. So the first thing is we're going to look at this particular function and we're going to determine whether Rolle's theorem is applicable or not. So again, mean value theorem, even though in the previous examples we did get that f of a minus f of b was 0 in the numerator. So here I could have actually also applied Rolle's theorem because f of 0 equals to f of 4. But mean value theorem could be anything, like my slope of my secant line can equal to any number, whereas for Rolle's theorem it's specifically 0. So let's look at this interval from 2 to 14. First, we look at our function f of x. You can see that it is continuous from 2 to 14. So we would say here that f of x is continuous on the closed interval 2 to 14. Because all we see here are smooth curves, that means that f of x is also differentiable on the open interval 2 to 14. The third and final condition is that f of a equals to f of b. So I'm going to do f of 2. F of 2 is equal to 2. F of 14, which is over here, is also equal to 2. Because these are equal, this means that Rolle's theorem is applicable. Let's look at this next interval from 6 to 14. From 6 to 14, we're looking at from here to here. It's the same exact function, so these first two conditions are the same. F of x is continuous on the closed interval 6 to 14, as well as f of x is differentiable on the open interval 6 to 14. My third and final condition, f of 6, must equal to f of 14. F of 6 is 10. F of 14 is 2. Because these are not equal, then Rolle's theorem is not applicable. And the reason for that is because f of 6 does not equal to f of 14. We always, whenever we are showing why something is not applicable, we always state why. And the reason is because of that third condition. These two numbers have to be equal. Now let's have a look at some of these examples. We have here for a, f of x is equal to sine of 2x over x plus 2, and we want to see if we can apply Rolle's theorem for -4 to -1, and if so, we're going to find the value of c that is guaranteed to exist. So let's start with continuity. This is a rational function, so that means that the denominator, x plus 2, cannot equal to 0. If I solve for x, I get that x cannot equal to -2. But that -2 is within this interval, so it already breaks that first condition in order to use Rolle's theorem. So here we would say that f of x is not continuous on the interval -4 to -1. And because it is not continuous, this means that Rolle's theorem is not applicable. And then we can't really do anything else after that. Now let's have a look at b. We have here g of x is equal to 9x squared minus x to the 4th, and we are checking to see if we can apply Rolle's theorem on the interval -3 to 0. This is a polynomial function, so with polynomials, we know that g of x is continuous on the interval -3 to 0. Also, because it's a polynomial, that means we're only going to have smooth curves, so g of x is also differentiable on the open interval -3 to 0. Now that third and final condition, we must show that g of -3 is going to equal to g of 0. So we're going to find those values. G of -3 squared is 9, times 9, 81, minus -3 to the 4th is -3 times -3 is 9, times a third -3 is -27, times a fourth -3 is positive 81. And 81 minus 81 is 0. And now if I find g of 0, we get 0 squared is 0 times 9 is 0, minus 0 to the 4th is 0. These two values here, g of -3 and g of 0, both equal to 0. Therefore, Rolle's theorem is applicable. And now we're going to go ahead and find the value of c. So just like with mean value theorem, the only difference is that once I take my derivative replacing x's with c's, this would be 18c minus 4c to the third. Instead of making it equal to the slope of the secant line, since I got that these two are equal to the same value, that slope of the secant line will be 0. And now we're going to go ahead and solve for c. 18c and 4c to the third, both are divisible by 2 and both have a c. So I'm factoring out a 2c. And that leaves me with 9c, just 9, minus 2c squared. If I make each individual factor equal to 0, I get 2c equals 0, and 9 minus 2c squared also equals 0. Here I would divide the 2, so c is equal to 0. Here I would subtract the 9, so negative 2c squared is equal to negative 9. Divide by negative 2. I get c squared is equal to now positive 9 over 2. And then square root both sides. So I get c is equal to plus or minus. The square root of a fraction is the square root of the numerator, which is 3, over the square root of the denominator. My interval is from negative 3 to 0, remembering that your endpoints are not included. So this c is equal to 0 is not my answer. Then here we have positive 3 over square root of 2. But positive 3 over square root of 2 is to the right of 0, so that is not included. But negative 3 over the square root of 2, negative 3 over square root of 2, the square root of 2 is 1 point something. So 3 divided by 1 point something is going to give you 2 point something, negative 2 point something. So this will be within the interval. So c is going to equal to negative 3 over the square root of 2. This would be my final answer. So you always want to check once you have your values of c that that value is within the interval, not including those endpoints. So now let's try a couple more. For each of these functions, we're going to determine whether Rolle's theorem is applicable. And then if so, we are going to apply the theorem to find the values of c that is guaranteed to exist. So for this first one, we have f of x is equal to x squared minus 5x plus 4 on the interval 1 to 4. So first we determine continuity and differentiability. This is a polynomial function, and as I keep saying, all polynomial functions are both continuous and differentiable. So f of x is continuous on the closed interval 1 to 4, as well as differentiable on the open interval 1 to 4. Next, my third and final condition is that f of a is equal to f of b. So we're going to find f of 1. Plugging in 1, we get 1 squared minus 5 times 1, which is 5, plus 4. 1 minus 5 is negative 4, plus 4 is 0. Now I'm going to find f of 4. 4 squared is 16, minus 5 times 4 is 20, plus 4. 16 minus 20 is negative 4, plus 4 is 0. Now it just so happens that coincidentally, both this example and the previous, those function values both equal to 0. But they could equal to anything. As long as they are the same number, then we can confidently say that Rolle's theorem is applicable. From here, now we apply the theorem to solve for that value of c. I'm going to take my derivative, and as I take that derivative, I am going to replace my x's with c. So x squared is going to be 2c minus 5, and I'm going to make this equal to 0. To solve for c, I don't have to factor anything here because this is linear, so I'm going to add the 5. So 2c equals 5, and divide the 2. So c is equal to 5 over 2, which this is going to be my answer, but I always like to verify and make sure that it is within my interval. 5 divided by 2 is 2.5, which is within here. Now let's look at b. For b, I have here f of x is equal to x raised to the 2/3 minus 1. Now, remember that your function, if it has a rational exponent, it will be continuous as long as the denominator of the exponent is an odd number. So I can say here that f of x is continuous on the interval -4 to 4. Remember that this is just another way of writing intervals. As long as the line is underneath, then that is the closed interval. Now I have to determine differentiability, and it has to be differentiable on that interval. So this may be a little bit harder if you don't have a graph. So I'm going to take the derivative and make sure that the derivative won't have a denominator that will equal to 0 within that interval. So f prime of x is going to equal to 2/3 x raised to the -1/3, which is the same thing as saying 2 over 3 times the cube root of x. Now notice that I do have x in the denominator, and if I set that denominator, remember that it cannot equal to 0. This is for differentiability. If I divide 3 to both sides, I get the cube root of x is still equal to 0. Raise both sides to an exponent of 3. I get that x cannot equal to 0, which 0 is within this interval. So here, f of x is not differentiable on the interval -4 to 4. And because it is not differentiable, this means that Rolle's theorem is not applicable. And I can't do anything else after that. All right, lastly, here what we're going to do is we're going to look at these theorems that we have just learned. We're going to read this question and we're going to apply these theorems through a chart. Sometimes in your questions, you're not necessarily told what theorem it is that you're applying, but you have to be able to determine what theorem is being applied depending on those conditions that are given. So let's start with A. Find the rate of change of h for the interval 1 to 3. So if I'm looking for rate of change, all I'm going to do is your rate of change that, and look at, you're given two x values here. What we're looking for is the average rate of change, which average rate of change is the slope of the secant line. So that's going to be h of 1 minus h of 3 over 1 minus 3. Now we are told here that f and g are differentiable and g is strictly increasing. The table gives values of the functions and their first derivatives at selected values of x. But here we're asked about h, but it tells you here that the function h is defined to be f of g of x minus 6. So in order to find these values, I first need h of 1, which is, I'm going to plug in 1 into the equation, f of g of 1 minus 6. In order to get this number, we have to work our way from the inside out. G of 1, if I come here, is 2. So I'm going to do f of 2 minus 6. And now I look, f of 2 is 9, and 9 minus 6 is 3. So that's h of 1. Now I'm going to do h of 3. So that's going to be f of g of 3 minus 6. G of 3 is 4. So I'm going to substitute that with 4. So now it's f of 4 minus 6. F of 4 is negative 1. And negative 1 minus 6 is negative 7. So now I can plug in these values. H of 1 is 3 minus negative 7, so it would be plus 7 over 1 minus 3, which is negative 2. This will give me 10 divided by negative 2, which is equal to negative 5. So this is my average rate of change. For part B, explain why there is a value of c for the interval 1 to 3 such that h prime of c is equal to negative 5. So here what they're asking is that what is the interval that will give me an instantaneous rate of change of negative 5? I got here that my average rate of change in part A was negative 5. And keep in mind what the mean value theorem states. The mean value theorem is that f prime of c, which I'm going to use h because that's this question, is going to equal to h of 1, or rather h of a minus h of b over a minus b. As long as your function is both continuous and differentiable, then MVT is applicable. Now here this is for h. They tell you that f and g are differentiable. If f and g are differentiable, in order for a function to be differentiable, it must also be continuous. So if you are told that a function is differentiable, you automatically know that it must be continuous. And since h of x is composed of f and g, then that means that h of x is also continuous and differentiable. Now we have found the average rate of change. I found this in part A. This is negative 5. So that means that over that interval 1 to 3, my average rate of change is going to equal to my instantaneous rate of change. Therefore, what I can say is that MVT guarantees a value of C such that h prime of C is going to equal to, and then what did I do here? I did h of 1 minus h of 3 over 1 minus 3. This is my reason why there must be a value of C, because the derivative is going to equal to my average rate of change. So when it says to explain why, it's basically because of MVT. Let's go to C. Explain why Rolle's theorem does not guarantee a value of C on the interval 2 to 3, such that, this should be h prime of C is equal to 0. So we already know that h prime of x is both continuous and differentiable. So those two conditions have been satisfied. The third and final condition for Rolle's theorem is that h of A must equal to h of B. So I'm going to find h of 2. H of 2 is going to be f of g of 2 minus 6. G of 2 is 3. So f of 3 minus 6. F of 3 is 10, and 10 minus 6 is 4. Now we're going to find h of 3, which I already did up here. H of 3 is equal to negative 7. In order for Rolle's theorem to apply, these two have to be the same exact number. Therefore, Rolle's theorem is not applicable And the reason would be because of that third condition, h of 2 does not equal to h of 3. Last question, find the equation of the tangent line drawn to the graph of h when x is equal to 3. So this has nothing to do with any theorems. I just wanted to practice this because it's been a while. In order to find the tangent line, we need the point of tangency, so h of 3, which again, I found that already in part A, which is -7. Then I would need h prime of 3. But before I can find h prime of 3, I need h prime of x. When I look here, my h prime is going to be, when I take the derivative, I need to apply the chain rule here, which the chain rule, remember, is the derivative of the outside function, so that'll be f prime, leave the inside alone, times the derivative of the inside, which is g prime of x. And the derivative of -6 would be 0. Now I'm going to find h prime of 3, so I know what my slope is. So that's going to be f prime of g of 3 times g prime of 3. G of 3 is 4. So this is going to be f prime of 4 times g prime of 3, which is 2. F prime of 4 is 3. And 3 times 2 is 6. So I have my slope, I have my point. So the equation is going to be y plus 7 is equal to 6 times x minus 3. And that's mean value theorem and Rolle's theorem.